All right, welcome to session 3 of the online Bug 3D training. Okay, today we're going to take a look at the Dambreak tools and then do some automation through leveraging the macro record feature and, a little Python scripting to make the components that we record within Bug 3D dynamic to automate a workflow. Okay, let's just start in Catapult here. First thing we're going to do is create a demo project. So I'm just going to create a demo project here, and I'm going to go with Pine River Hills to start. I've created this project many times before, so I'm going to give it a unique name. So I'm just in Catapult, as usual, created a demo project. So just up here, created my demo project, and I'm going to go with Pine River Hills. And I'm just going to give this a unique name. Hit OK. And pick my license. So we're going to start by looking at the Dambreak functionalities, the Dambreak tools, and then from there, do a little automation by leveraging that macro record feature, recording within Python, the different tasks that we're doing, the different functions that we're using, and then taking those components, uh, combining them and making them dynamic through a little modifications in terms of the scripting. But let's start with the Dambreak tools. Okay, so Pine River Hills, once again, I'm going to start by building a base topographic surface or original ground surface. Going to take this LiDAR data, throw that in there. Surface from layer, choosing that LiDAR data that I just loaded. All right, I have my surface here. I don't really need a surface, I need a grid. I'm going to take this surface and construct a grid out of it. Grid, create grid from surface. Select the surface of the LiDAR data we just processed. I'll keep that 10-meter spacing, that's fine. Hit OK. And maybe call this LiDAR underscore grid dash 10-meter. Just so I have that grid spacing noted in the name. All right, so I have my grid. I'm going to save that. Close down my surface. I don't need it. I don't need it saved. And I don't need my LiDAR data anymore. Okay, so the first Dambreak tool we want to take a look at here in the Dambreak menu, sandwiched between ooze and dam templates, is fail a dump. So let's start by failing a dump and then take a look at a tailing storage facility. Okay, so I need to construct a topographic surface with a dump in it. So I'm just going to use the structure tools to do that. So I can see I can build a dump from the crest or the toe. Taking a look at my elevations here, I'm in that 90 to 125-meter range. So I'm going to just create a crest line at about 135 meters in elevation. As I just let people in here, 1 second, please. Okay. So polyline, create, draw a rectangle. We call this the crust. I put this at 135 meters in elevation. And I'm going to just place it right there. Doesn't really matter where you place it. Then going to take my structure tools, dump shell for crest. Put a 3-to-1 on that. We call that dump shell. And I'm going to merge it into my grid to create that dynamic model, or at least a grid with the dump structure already built in. Select my dump crest, select my base grid. Give it a moment. All right. We now see that we have our grid surface here. Our original grid with the ladder grid 10 meters now been modified. That would red float with a dump facility merged in. So I'm going to save this. Going to give it a unique name to differentiate it from the original ground surface. Ladder grid. So I close down these. I don't need them anymore. And I'll start working with this surface and my original ground surface. Okay, let's take a look at fail and dump. All right, so 4 parameters here that you define when failing a dump. Your run-out slope, failure slope, breach width, and breach elevation. Okay, so run-out slope on a percent basis. So here you're defining as the material is leaving the dump, at what slope is it going to sit on the original ground? So it's almost the angle of repose as material is leaving. What is that material going to sit at after it's breached your facility? The failure slope, breach width, and breach elevation. Here you're all defining the trapezoidal channel where the breach will occur on the dump. Okay, so in other words, if we take a look at this cross section here, we have the breach width. So this is a cross section through your dump. That's what you're looking at here. These 3 parameters, you can see them here. So you're defining this trapezoidal channel at which your dump's going to fail. So you're defining this, the breach width, the breach elevation, and that cross-sectional slope here, which is your failure slope. And then your run-out slope is going to be essentially the angle of repose the material is going to leave your facility at. What's it going to sit at after it's left the facility? Okay, so I'm going to do a run-out slope of 4%. So we said that material is going to be sitting at 4%. A failure slope of, let's say, 5%. So this is going to be a 5% slope here. My breach width, I'm going to say the base is 50 meters. So 50-meter breach width. And the breach elevation. So my crest, I drew it at 135 meters in elevation. So I'm going to say this is going to fail at 120 meters. And if you just hover your cursor above these different fields, you'll notice this data type listing appears. And this is just to let you know, basically how many variables can you put in here? Can you put in a range? Is it just a unique value? In this case with fail and dump, all of these parameters are decimals, so they're unique values. So you can put in one value for each per fail and dump run. So I'm going to hit OK. So it's asking me to select my dump grid. So right now, I can see that I'm not really selected by dump grid. Now I am, because that dump is highlighted in red. So just to be sure that you have the right grid as you're selecting them, I'm going to turn off my original ground surface, its visibility. So the software only has the option to select the grid with the dump in it. Because in this function, you need to select a grid with a dump present, and then a grid with the dump not present or your original ground surface. Okay, so I'm going to select my grid with the dump present. Now that it's selected, it disappears, no longer an option. I'm going to turn back my original ground surface, and I'm going to select my original ground. Okay, now I'm going to draw breach alignment. So here we're placing a cross-section line, or a line that's going to be perpendicular to my dump face, and it's going to define the X and Y location of where the breach is going to occur. We've already selected the elevation at 120. So I know that the elevation of the breach is 120. This is just selecting, in X and Y where that's going to occur. And what's important here as you draw this line is you have to make sure that you contact your dump at that breach elevation that you chose. So I can't just draw a line over here, right? Because I'm not intersecting my dump, and I'm not intersecting my dump at that 120-meter elevation that I chose. And even if I came down here and I made a little line there, I wouldn't be contacting my dump at 120 meters in elevation necessarily, right? 120 meters in elevation is somewhere in here. This is 135. This is original ground. That's at 98. So somewhere in here is at 120. So here I'm just going to make sure that I, make a line that for sure contacts my dump at 120 meters. I'm going to hit spacebar when I'm done and just let it run. Okay, we can see here a number of new layers have been created. So let's just go through them. I'm going to turn off the visibility of my grid with my dump. I'm going to turn off the visibility of my original ground surface. And I'm going to take a look at these one by one. Okay, so first I have this tailings failure grid. Okay, and this shows how the dump failed. It doesn't show the material that left the dump, but it shows how this dump failed. So we can see here, if we get a pad, keeping in mind that we're at 3-to-1 vertical exaggeration, you can kind of see here that 50-meter breach width, but that 5% failure slope. And here this is, if you look at the cursor at the bottom left corner there of the screen, you can see the coordinates. This is at 120 meters in elevation. So this is what we defined in terms of that trapezoidal channel. You have 5% here, 50-meter here, and this was at 120. And that's what it created. Next, we look at the source point. Okay, this is that 120-meter elevation location where that line that we drew, that cross-section line, intersected the dump at 120. Okay, we have the output grid here. This shows both the failure on the dump and the material that left the facility there. And the outline. So this is just defining, where the material went. I think you can see it in the grid, but you can also, have that outline. If we take a look at the outputs, it's giving us, like when we do a deposition run, maximum runout distance, average thickness of tailings, the maximum thickness of tailings. So there's a maximum of 10.6 meters here. The distribution of the thicknesses, the total volume that left. So you can see here we lost 668,000 cubes. The material backs up to an elevation of 113 meters. So this would be right there. So this is where that, failed material contacts the dump here is at 113.07 meters. But here the volume and tonnage, same. The breach elevation is 120 as we defined it. And here we have the maximum runout distance. So traveled a maximum of, 393.8 meters. And that's fail a dump. And it requires two surfaces, original ground surface and a surface with that dump merged in, or grids, I guess. A grid of your original ground surface, or a grid of your original ground, and a grid of that original ground with the dump merged in. Right, I'm going to clear my screen. Discard all. And I'm going to bring back my original ground grid. And this time, build a TSF here. And pour some tailings, and then fail a TSF. All right, so for this next function, for each tailing dam, we need 3 grids. We need this original ground, which we have. We need a grid with just a dam built, no tailings, or what we want to consider being, freshly placed tailings. And then we need a grid with the dam plus tailings. So let's start by creating, just a surface with a dam merged in. I'm going to just do this quickly by drawing a dam. That's at 135. Wait, 125. 20 meters, 2 to 1, 4 to 1. Shell height 50 meters, and I will create a dynamic model so I get that merged grid immediately. So my TSF. All right, I'm going to save that now. I'm going to create a new working directory as this is getting a little chaotic. To save that merge grid, I'm going to call this grid plus dam. I'm going to quickly draw a discharge line and define a tailings type and pour some tailings into here. So ooze, discharge points, draw regularly spaced discharge points. I'm going to place this a couple meters below my crest at 122. And I'll keep 100-meter point spacing. Just quickly here, point there, right there. Right there. Here. Here. There. And then C to close. Save that into my working directory. I don't need my dynamic model window anymore. And I'm just going to pour some tailings. But first, let's create some tailings. Project, tailings database. Ooze project, tailings database. Right-click new. Call this tailings. I'll keep my densities at 1. Above water, 1.02. Sorry, 0.02. Below water, we'll go 0.03. So 2%, 3% slopes. Hit OK. I'm going to just quickly run a capacity model. Just fill this with tailings, no water. Ooze, single stream deposition, no pond, as we're not really accounting for the volume of the pond in these dam break functions. You know, it's assuming a sunny day failure here. We're really just taking into account the volume of tailings, the embankment structure. You know, even if we created a pond here, it would be relevant towards the functionality. All right. I was just checking the chat quick. Single stream, no pond. We'll go as drawn. Pick this grid with the dam merged in. Choose those discharge points. We only have one tailings type. We've selected it. Hit OK. So we can see here we've created our output grid now. We have tailings. That's going to be saved automatically to our working directory, so I don't have to worry about saving that. And let's just keep the layers open that we need now. So to get any of my original ground surface, I'll keep that. I don't need the dam center line anymore. I'll close that down. Dam shell, I don't need it. And I've now unloaded all of them but that. So let's reopen. Grid plus dam. Output grid. And original ground surface. All right, let's run breach tailings dam. So same concept here generally as the fail a dump. We're going to define that trapezoidal channel of failure. But we're distinguishing between, you know, the tailings material here and the embankment structure. With the dump, there was just, you know, one type of material that we were assuming, you know, whatever was in that dump, you know, whether that be tailings or, you know, waste rock. Here we have, you know, two different components. We have the embankment structure itself, and then the tailings material. Okay, so once again, we have that run out slope. So at what slope will, when that material leaves the facility, you know, how will it be kind of that angle of repose would be sitting at. I'll go 4% again. Once again, we have that failure slope, breach width, and breach elevation. So we're going to be defining that trapezoidal channel within the tailings as to how it's going to fail. So I'll do 5% again, breach width 50, and breach elevation. I believe I'm at 125 here, so let's do 110. And then dam failure slope. So within the tailings facility, how is it going to fail as opposed to within the tailings? Or within the embankment structure, how's it going to fail as opposed to within the tailings material itself? So we're distinguishing here between the two. So the tailings will fail at 5%, and we'll say that the cross-sectional slope here within the embankment structure, we could fail that at, say, 3-1. Hit okay. So here it's asking you for your tailings grid. So your tailings grid is your output grid. It's your grid with the tailings merged in. So I'm gonna turn the visibility of those other two surfaces off and choose my output grid. It's asking me for grid plus dam. So original ground surface plus the dam. So this is how it's distinguishing between, what it wants to consider as, TSF material that's being contained within versus the embankment structure itself. And then it wants the original ground surface. Again, it's asking me to draw the breach alignment. So what I need here is to ensure that this line that I draw perpendicular or, crossing my TSF, intersects the TSF at that elevation. So the elevation is already defined at 110. I just need to make sure that this line, as I define the X and Y where the breach will occur, intersects the embankment structure at that elevation. So just want to go through it just to make sure you hit it. Hit spacebar. Let it run. Okay. So once again, it's created. The tailings failure grid doesn't show the material that's failed, where it went, but shows how that breach affected the TSF. Okay, so here we can see that trapezoidal channel. And we can see how we've defined it within the embankment structure and within the tailings. So we see that 3-to-1 slope here that we set. The 50-meter breach width. That 110-meter elevation. And then we also see the 5% slope that we set in the tailings. So the only difference here between fail a dump and this function here, breach a tailings dam, is we get to define different slopes for material within the TSF versus the embankment structure material. So it fails differently. This fails at 3-to-1, the cross section. This failed at 5% based on what we input. And having that option to pick that additional surface, the grid plus dam and the output grid with the tailings merged in allows us to do that. And we have the output grid, which shows both the failure within the TSF and the exiting material. And once again, the outline. The outputs, the same, showing us, how much material left, what elevation does it back up to, what's the maximum runout distance, what are the thickness percentiles. Okay. Let's do another function. Clear my graphics. And take a look at estimate write-out volume. Okay, I'm going to reopen my original ground surface, my grid plus dam, and my output grid. Dambreak, estimate write-out volume. Okay, so this function is a little different. And that one we can enter ranges of values. So it's not just single variables. We can do ranges or multiple values, and then run the function for many scenarios. If you hover once again your cursor over the various fields, it lets you know, can I enter a range? So for the tailings failure slopes, here I see I can enter a range of values. For the dam failure slope, I can only enter one value. It's a decimal. For the breach elevation, once again, I'm back. I can enter a range of breach elevations, but for the breach width, once again, just a single value because it says decimal. So range, multiple values, uh, decimal, one value. Okay, so here I want to assess as this facility fails, uh, multiple values. But first, I want to close down my output grid here because I've overridden the output grid that I need. The situation essentially is after I run the Dambreak function, it creates a grid called output grid that shows, the material failed within the TSF and where it went. But I need my output grid, pre-failure. So a little sloppy on my part there. I should have created a new folder for this output grid and the results to go to. Instead, it overwrote, my original output grid pre-failure. So I'm just going to rerun a deposition to recreate my output grid. It's quickly ooze, single stream, no pod, as drawn. Last value for all fields. Run this again. Now I have my pre-failure output grid. Gonna unload my tailings outline and my discharge points. I don't need them. And run this function. Okay, Dambreak, estimate runout volume. Okay, so here I have the option of doing a range. So what would a range look like? If I want to assess, how this is going to fail for multiple types of tailings failure slope. So after this leaves the facility and the material's sitting at various elevations, after it's failed, I want to assess it from 1 to 4%. So that would be 1 to 4%. The comma is saying go in a range. So do 1, 2, 3, and 4. If I wanted to do 1 and 4%, I would put a semicolon. So this will do 1 and then 4. So comma, range, semicolon, and. So basically the comma is 2, 1 to 4. Semicolon is 1 and 4. So I'll do 1 to 4. So I'll do multiple scenarios. It's going to fail. It's going to say 1%, 2%, 3%, 4%. And then in terms of the slope, so how that breach is going to look through the facility, how that trapezoidal channel will be defined through the facility, I'll say 6 to 1. Breach elevation, once again, I'm at a range. So this goes up to 125. So I want to see it for 105 and 110. And my breach width, Single value, I'll keep it at 50. I'll hit OK. So it's asking me for my tailings grid. So just to make sure that I'm selecting the appropriate grid, I'm gonna only have my output grid open. Grid plus dam. There it is. And original ground. I'm gonna draw the breach alignment. I'm gonna draw it right there. And I'm gonna hit spacebar when I'm done. You'll notice here new folders being created. And the folders are being named one for the elevation, the breach elevation, and then for the tailings failure slope. So I asked it to do 105 and 110 from 1 to 4%. So it's going to run through 105, 1 to 4, 110, 1 to 4. You can see it's done. The results not in your output window. The results are here in this Excel file that I created called Runout Volumes. Take a look at that in a second. I'll just clear my graphics quickly. So in every folder now, for every breach elevation, tailings failure slope, you have the dam failure grid showing, how it failed on the facility. And the tailings failure grid showing, how the material left. So you can see here, you've lost some material. So if I toggle the visibility of my dam failure grid on and off, you can see a difference in the amount of tailings in the facility. So it's showing you how the tailings failed and how that dam failed. With your tailings failure grid essentially having the failure components of the retaining structure and of the tailings within it. But we don't see where it went. You have this for every option. So you don't see where the tailings went with this tool, but you see how it failed within the facility. And it's summarized in this Excel sheet that I'll just open up right now. So you see here, once again, breach elevation, failure slope, breach width, failure slope, and dam. So these, once again, failure slope and dam, breach width, these were decimal inputs, so you could only do one. And the breach elevation and failure slope, you could do multiple or ranges, and it'll run through every different combination based on what breach elevation or failure slope you picked. It's giving you the volume total of dam plus tailings that failed, and then it's segregating it between tailings and dam based on the input parameters. So if you want to create a lot of numbers quickly in terms of values, volumetrics, of material that left the facility for a lot of ranges, this would be the tool. I'm going to close this down, clear graphics. Then we can do estimate runout volume, no dam grid. Okay, for this one, I'm going to go back to my dump. Original ground with my dump. So this tool is the same as the previous tool, except you don't need that additional surface with just the dam. You need that original ground surface, and then your facility as it exists, with the retaining structure, with the tailings, but you were not using a surface with just the dam built. And that means there's going to be no segregation between material within the TSF and a retaining structure. It's treating everything as one material type. So I'm going to use this for a dump. So again, I hover over the input field here, and I see I'm dealing with a range. So I'm going to go flood to 5% and my breach elevation. It's giving me a range for the breach elevation now. I'm going to say I could go from 100 to 105. I should this up with 35. Yeah. 10. So I'm going to do multiple failure slopes and multiple breach elevations. Run all those scenarios. It's asking me to select the tailings grid. So that's just going to be my grid with the dump merged in. Just isolate it and make sure it's selected that one. Layer drawn around surface. And then just quickly draw my breach alignment. I'll draw it over here. You can see how this is happening. Let's create a number of new folders. For every breach elevation and every failure slope. Okay, it's ran through every iteration. You can see here in the Project Explorer. So every breach elevation, every failure slope is in its own folder. If I just clear my graphics here, take a look at the results. So we did 10 different breach elevations, 5 different slopes. So a number of folders have been created, each one containing the failure grid, failure outline, and the tailings failure surface, which is a large cone slicing that original grid. So we can see here, if it failed at 100 meters in elevation at 1%, you're losing a significant amount of materials, kind of just really taking the whole thing off. And then if we come down here, 110 at 5%. Let me just save this so I can save this under a different name so I can visualize them both at the same time. See that difference there. I'm just gonna put a cross section through here. And let me just open up my original ground as well. So just taking a look at a cross section through the failure area. You can see here our original ground surface. Here's our in green the surface with the full dump. But we can see here, at 110 meters, 5%, this entire corner here shears off. And I believe what we're seeing here in terms of this first surface, failure grid 1, or the 100-meter failure at 1% is, basically this entire piece of the dump fails. I think if I extend that cross section, we'll be able to see that. Yeah, so you can see kind of you're losing almost everything in that first scenario in terms of your dump volume. But at 100 meters, 5% failure slope, so kind of losing this full corner here. So it creates that surface once again for every duration. It doesn't show you where the material went, but it shows you how it failed. And volumetrically, once again, everything's going to get summed up in runout volume Excel spreadsheet. Just give you that breach elevation, the failure slope, and every time the total volume. This time, no segregation between, tailings volume and dam volume because there's only one material type. We didn't pick a dam grid and an output grid with tailings in it. You just picked one grid with the facility, and all those volumes are listed here. So that first scenario, you lose, 27 million cubes, and that last one we saw, with that corner kind of getting sheared off, that's 1.146 million. All right, I'm just gonna clear my graphics again, bring back my original ground surface. Here I have a lot of folders. Maybe I want to rerun one. I don't want to have to delete these all manually. You can come to Dambreak and go clear run out volume estimate runs. This can't be undone, so it's asking me again, are you sure you want to do this? You have to select that. If you don't select that, it just won't run. Hit OK. And then I'll just slowly start removing each of those folders so you don't have to, delete them manually. Okay, I'm going to create a new folder here within my base folder. Dam face. So I'm going to open up that original ground surface. I'm going to put a little dam here. I'll draw it. Let's say 115. Keep these parameters the same, create a dynamic model, so it gives me that grid with the dam merged in immediately, just like my base. I'm going to draw it across here. Don't really need to play around with it, so I'll close down my dynamic model, and we'll just save that merge grid. Dam grid. Unload these. And then I'm going to run this run up from dam face function. So here, once again, you have the option to enter a range of values. So you're entering a range of failure volumes. So if this dam were to fail from the face with these volumes of material at these failure slopes, where's the material going to go? That's what this function is going to tell you. You tell it the volumes, you tell it the failure slopes, and then it will give you the footprint and location of the material as it leaves the face. And you define where in X and Y it's going to leave the facility, X, Y, and Z. You pick a point. Okay, so for volumes, I'm going to say I want to go 100,000 and 200,000 and 500,000. And I want my slopes to be 1 to 3%. So semicolon, so 100,000 and 200,000 and 500,000, and then 1 comma 3, 1 to 3%. So do 1 to 3%, 1, 2, 3 for each volume iteration. That's going to be use selected point elevation. So I'm going to select a point on the dam face as to where it's going to fail. I want it to use that X, that Y, and that Z. And I'm going to hit OK. I'm going to select my grid with the dam merged in. And I'm going to say it's going to fail right here. Okay, so once again, created a number of folders, and each folder corresponding to an option that we entered. So for each volume value, do that failure slope from 1 to 3, 100,000, 200,000, 500,000. It's created line work showing every permutations failure footprint. We also have the output grids. So this is showing where the material goes for each option. So you have outlines of where the material goes. You have, topographic surfaces showing where the material is. And as well, this readout summary spreadsheet that it creates with the numbers summarized. So for every volume and slope combination, max beach elevation, min beach elevation. So the maximum, elevation of the failure surface or the failure area, the minimum elevation of where, that material backed up to, how far did it go, the minimum run out distance, and the difference in elevation from source to the beach. Again, if you want to take these folders out, go to Dambreak, clear, run out distance runs. Check to delete. Now we'll remove all those folders for you so you don't have to delete them yourself. But you'll notice it left the run out summary spreadsheet. So it'll get rid of those iterative folders or those, scenario specific folders, but it'll leave the spreadsheet in. And that's essentially the Dambreak tools. Um, depending if you want to segregate, your retaining structure from the tailings within, you either use breach a tailings dam or fail a dump. If you want to do multiple scenarios, that's either estimate runout volume or estimate runout volume with no dam grid. So if you have a dump one material type, use no dam grid, use the fail a dump. If you have retaining structure and tailings, you want to use breach a tailings dam, estimate runout volume. If you just want to, if you just have a structure, you're not really, you know, you're not really looking at, how looking to define the failure channel through the facility itself. You just want to know where material will go based on slow properties and total amounts. Use runout from dam face. These three here allow you to run multiple scenarios at once for different combinations. And these, you define that failure channel more specifically, but you can only run it one at a time. All right. Declare my graphics and move on to some, coding automation. Okay, let me bring back in my original ground surface. Let's start a new folder. I'm going to copy this over, copy to working, and bring that in. All right, so first thing I'm going to do is just run through the process quickly. So I have a multitude of, you know, crest elevations, pond volumes, tailings volumes that I want to, run scenarios for to see if I'm going to have enough freeboard. So let's take a look at them now. So here I have, a dam. I want to build it to all these elevations, and I want to see what happens if I place, this much tailings per lift, and these are going to be my pond volumes. So I want to build it to 110. I want to have 400,000 cubic meter pond, and I want to have 2 million tons of tailings put in. Then I want to build it to 112. My pond volume is going to go up to 700,000, and I'm adding another 2 million tons of tailings. And I want to run it from 110 to 121. So I can do this manually, do it for every iteration, look at the results, check my freeboards. Or I'm going to do it once, record it, and then modify the script a little, or maybe a lot, to make it dynamic so I don't have to, re-go through the same process. Because essentially I'll be doing the same thing, build it up, pour some tailings, this is my pond volume, take a look at it, maybe take a snapshot, take a picture, and then do it again and again and again. So to accomplish this in a more streamlined fashion, I'm just going to leverage the macro import feature. But before we begin, I'm building a dam structure up to multiple elevations. I want to take advantage of the dam template feature. All right, so I'm going to begin by, defining a dam template. So first, I'm going to pick a general location. Let's say my dam is, somewhere over here. Just going to draw it quick. I'll drop to 115, 20-meter crest width, 4-to-1 downstream, 2-to-1 upstream, 50-meter shell height. Create that dynamic model. Select my base grid. I'm going to place my dam in here. Right here, I'm going to hit C to close it. Okay, so this is going to be my dam location. What I really need right now is that center line. So I'm going to unload these two other layers. And I'm going to keep my center line. So this is going to be the center line of my dam. I'm going to say this is a center line dam. So the center line is always going to be valid in X and Y. And I'm going to save that. Dam center line 115. Right? I'm going to go to dam templates, setup, dam profile manager. I'm going to define a generic cross section for my dam here under fixed width centerline. I'm going to call this CL. Downstream slope 4-to-1, upstream slope 2-to-1, crest width 20. Skirt height, so the height of the unclipped shell. Just need to make sure this is sufficient to penetrate topography. We go 75 meters. And I don't need to worry about cutbacks here. Hit OK. Save it. Then I'm going to take that generic cross section and reference it to a specific design line. In this case, my center line. So that generic cross section is always going to be applied to this center line. And because this is the center line dam, that works. So it's just going to progressively, as I apply a dam template, build that dam up to different elevations based on that cross section at this location. Dam template setup, dam template manager this time. Single profile dam. I'll create a new one. Call this center line. It's asking me for a reference line, so it's going to be this line I'm looking at on the screen. What generic template do I want to apply? Well, I only define one, CL, so I'll apply that one, and it is a closed dam. Hit OK, and I'll save it. Okay. It's back here. Look at my graphics. And now I'm going to start the recording process. Okay, so I want to do my first iteration. So I'm going to start with building it up to 110 meters in elevation. I want a 400,000 cubic meter pond. And I want 2 million cubes of tailings. So I'm going to record script. So right now, everything I'm doing within Tailings Plus is going to get transcribed into a Python script that I'll be able to edit after it's complete. Okay. First thing I'm going to do is I'm going to go to project, use project, new deposition run. I'm going to call scenario training. And my year is going to be my first crest elevation. So I'm doing this right now because this is going to create a root folder and a subfolder. Root folder is going to be called training, and the subfolder is going to be called 110. So this is something I'm doing to essentially just create folders. I'm going to make this dynamic after, so it's going to create a new subfolder at every crest elevation. So really this is just about folder creation. Next thing I'm going to do is I'm going to raise that dam. I'm going to raise the dam to 110 on my original ground surface. And I'm also going to create a discharge line when I do that. Also notice it created a 𝐓𝐸𝐲 folder here, traded, and then 110. And this is a structure we'll be able to repeat and leverage. Okay, dam templates, dams, raise dam. I want to pick that center line template that we created. We're going to go up to 110. My base grid is going to be my original ground surface. And then there's no cell boundaries. In advanced, I will to create a discharge line. I'm going to create it 1 meter below my crest, and 150 meter point spacing is fine. Hit OK. All right. Created my dam at 110. I'm going to pour some tailings as per my specifications here, which is 400,000 cubic meter pond, 2 million tons. Before I do that, though, so I don't overwhelm my screen, I'm going to clear my graphics. I'm going to go to 𝐓𝐸𝐲, single stream deposition. You'll also notice after we applied that template, it created a centerline folder in our working directory with that grid plus dam surface. 𝐓𝐸𝐲, single stream deposition. I have a fixed pond volume. And I have a volume target for my tailings. So I'm going to be using flow path down slope. My base grid is going to be the grid with my dam merged in. My discharge points, I've created them when I applied the dam template, and they're also in that template folder, dam discharge points. My initial discharge elevation, I'm going to say, is 109, where the discharge line was created. Tailings tonnage, let me just check that again quickly. It's 2 million. Don't have to worry about elevation changing or having an offset when I pour. Initial pond elevation guess. I'm gonna guess 5 meters below my crest, so 105. And my pond volume, pretty sure it was 400,000. Max contained. I'm gonna say it's 109 as well. 1 meter below my crest, and I should be good to go. Just gonna pick a point inside my GSF. All right. I have my output grid now with my results. Let me clear my graphics. And now I want to do something to visually represent that deposition sequence. And I'm going to do that by leveraging a satellite photo that I have and the output grid. Okay, so here I'll just go back to my 𝐓𝐸𝐲 directory here. So after my deposition run, It's created my output grid. Tailings outline. So I know where the tailings is located. I obviously have the output grid showing the dam and the tailings. And in my centerline folder here, I have this footprint line work, which defines the footprint of where the dam's located. So I want to take that satellite image, modify it to represent that there's now a new dam there and that there's tailings. The pond itself can be represented through, the pond surface. I can just open that up. That'll make it look nice. But I need to edit that satellite photo to show that there's now a dam structure and tailings placed. So I have line work relating to the footprint of the dam and to the footprint of the tailings. So I'm going to use those to modify the satellite image. So I'm going to go to the text, create, pen overlay with colors. This function is, once again, I'm going to edit satellite imagery to now represent that there's a dam and some tailings. And I'm going to do that in every time step so we can see that evolution. Okay, my base image is going to be my, original satellite image unmodified. So I'm going to go find that. It's in my imagery folder. It's at 𝐓𝐸𝐬𝐬. I'm going to call this image underscore 110 meter. My first outline is going to be the outline of my dam, which is in that template folder and its footprint. I'm going to make it brown. Come here in this left-hand column. I'm going to add one row. And now I'm going to define, what tailings area I want on the image to be modified. That's in my active folder. It's tailings outline. And I make that this goldenish color. Then we hit OK. You can see here in my working directory, it's now created a 𝐓𝐸𝐬𝐬 file and a JPEG as per my modifications. I'm going to take a look at that. I'm going to open up my output grid, drape on my modified image. And I'm going to open up my pond surface too. So you can see here now we've updated the satellite imagery to represent the dam, tailings, and the pond. I'm going to choose a perspective that I like here. Yeah, we don't want to go back to this perspective at each iteration to represent the evolution of the pond. Maybe not that one. Maybe like this. So I want to go back to this viewpoint every time. So you can see that relative evolution. So I'm going to save this as a viewpoint. Viewpoints, save current viewpoint. Call this view 1. So if I leave now, and I want to go back, I can just restore it. It'll take me right back there. And I'm just going to, save this. View, save image. I'm going to call this screen grab 110 meters. actually going to save this as a JPEG in my working directory. I'm going to stop my recording. Okay, so everything I just did now has been transcribed to this Python code. So I'm going to take this code, make sure I grab it all, and I'm going to put it in my script editor. So the formatting is a little more straightforward. Okay, so if we review the code here, we can see every component of what we just did. So to start, we started that new deposition run to create the folder structure. We called the main folder the scenario training, and then the year was 110. So I go back here, that was just going 𝐓𝐸 project new deposition run. We called the scenario training. We called the year 110. And that gave us our initial root folder and subfolder. Then we applied the dam template. Centerline dam. We chose to create a discharge line 1 meter below the crest. It was 150-meter spacing on the points that we set. And we chose to raise it to 110 meters crest elevation. And this was the location of that initial base grid that we chose to raise our dam on. We then cleared our graphics. And here we did the deposition run. So this is single stream, fixed pond volume, flow path down slope. It says auto flow path in the code, but it's flow path down slope in the software. We assume no discharge line offset. Here's our 400,000 pond volume. This is the initial discharge elevation that we chose. We don't worry about max change or max iteration. That's just how the software is going to run through different iterations. We didn't change those. We just leave them as is. We considered our maximum containment elevation to be 109. Here it's listed as maximum pond elevation. The software is the maximum containment elevation. This 1 meter max pond elevation change, once again, just defining how the software is stepping through different iterations. We don't have to worry about that. And more here settings of the different iterations, which we didn't really touch. Our pond guess was 105. That's the 105 here, pond elevation. This is the error tolerance on the pond, set to 1%. This is the location of the pond at X, Y, and Z. This is the point we picked on our screen when it's asked us to pick a point at the pond. Another error tolerance here of 1% on the tailings. And this is our tailings value here, 2 million. And we opted to not use direct deposition. Again, we cleared our graphics. And then we began the process of modifying that satellite imagery. This was the original satellite image that we chose, that PRH in the imagery folder. These are the two pieces of line work that we chose. The center line within the dam template folder center line, we chose that footprint. The dam footprint. This is the color that we chose to make it, brown. Then we went and we got the tailings outline out of our working directory, and we made it that goldeny color. And then we called it image_110. After the satellite image had been appended, opened up our output grid here. Open geometry, output grid. We took that satellite image that was appended, the image 110 𝐓𝐸𝐬 that we created up here, draped it on the output grid. Then we opened up our pond surface. We saved a viewpoint. We restored the viewpoint. And then we saved the picture. We called it screen grab 110. And it's a JPEG. But that was the process. Okay, so just right off the bat, I'm not going to need to re-save a viewpoint for every iteration. So I'm not going to need this piece. I'm just going to get rid of it. My script. I will need to restore it and go back to that view, but I don't need to create it and save it. It's already created. It's already saved. So I don't need to redo that. Okay, so let's start by defining our variables. Okay, so these are all the values that I want to do. I've done this one. Let's check. Now I need to do 112 to 121 with these different permutations. Okay, so I need to define that within the script. So I'm going to start by bringing in, this is a little less straightforward, but I need to bring in an API here to set a working directory. And these are libraries of functions. So this is just giving me the ability to make a folder, the working directory. So as we're going from 112 to 114 to 116 meters in crest elevation, we're going to be going to new working directories. So I need to incorporate that into the script so that it has the ability to do that within the software. Okay, so first thing I'm going to do is I'm going to define my previous elevation that we just went to, which is 110. So that's the previous elevation. We already did 110. Okay, now I want to make a list of all the future elevations I'm going to go to. Just making a list here. 112. I want to go to 114, 116, 117, 118, 119, 120, 121. And now I have all the pond volumes. I'm going to call that list li fluid volume capital V. Open bracket. So next I'm going to 700,000 pond volume. After that, 1 million. Make sure I got my numbers right. All right. Then 1.2 million. 1.4 million. 0.7 million. 0.8 million. 1.8 million again. And 1.8 million again. Okay, so it covers my elevation range, my pond volume range, and I'm just gonna make sure I have the right amount. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And now my ranges for my different values for my tailings. I'm gonna call this Li tonnage. Open bracket. So I'm going to 2 million next. 2 million again. 2.4 million. 2.4 million. 2.5 million. 2.5 million. One more 2.5 million. Reducing production 2 million. And finish it off with 1.5 million. Okay, so I have my previous elevation defined that I went to 110. Upcoming crest elevations, upcoming pond volumes, upcoming tailings volumes. Now I'm going to open up a for loop so I can cycle through all these values. So for elevation, so I have to create a new variable now, elevation. So for elevation, fluid volume, another new variable, fluid volume, and tonnage in zip LI elevations, LI fluid volume, capital V, and LI tonnage. Okay, so what I did here is for this variable, which I've just created, for this variable, which we've just created, and for this variable, which we've just created, in these three lists. Now this zip is, it's like it's creating a table now. It's basically recreating. It's recreating this table. The zip is now linking these values together. So it's going into LI elevation and saying, okay, you're at 112 to start. What's the first value for fluid volume? 700,000? What's the first value for tonnage? 2 billion? Okay. Like these. This is all one row. And then we're going to go to 114. And we're going to look at the second value. And then 116. And the corresponding values. So it's looking at it in sequence. So it's linking them by order that they're listed in their lists, respectively. There needs to be the same number of items in each list for it to work. So this had 7 items, and this had 8, and this had 9. That would work. So there's 8 in each. 1 second, let me count that. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's one extra here. Let's take that out. Let's count that again. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Debugging. So it's going to link these in a table. Now I want everything to exist within the for loop. So I'm going to select everything below that for statement and just tab it in. So now it's inside the for loop. Otherwise, it would be outside the for loop. Okay, so the first thing here is I'm creating the folders. So the advantage of doing that system where I went through ooze, project, new deposition run, was it created this root folder and a nice subfolder called 110. Well, I definitely want the different lifts to go into folders named after what that crest elevation is. So they can't all go into a folder named 110. That would already exist. So the next one, I want it to go in a folder called whatever elevation I'm at in my for loop. Whatever elevation I'm at in my for loop, call it that. But I can't name something a number. You know, it needs to be characters. It needs to be a word. So I'm going to take that number and I'm going to turn it into characters by entering it as a string. Now, it's fine that they all go into, well, it's preferable, it's desired that they go into a main folder called trading. So they're all going to go into that root folder called trading, but then for every run, it's going to create a new subfolder, and the subfolder is going to be called whatever crest elevation you're at. Okay, next, I'm going into my raised dam. So I always want to raise the dam. I always want to use that centerline template. I always want it to be 1 meter below, or I want that discharge line to be 1 meter below my crest. I want the discharge spacing to always be 150 meters, but I don't want to raise it to 110 meters every time. Obviously, that needs to change. If I'm in the 112 scenario, it needs to be raised to 112, so on and so forth. So this value is now the variable elevation. So wherever I am, I'm going to raise it to that elevation. Okay, here. So for this first run, it was fine to use the original ground surface. But for future iterations, I want to be building off the output grid from the previous run. So next, when I raise that dam to 112, I want to raise the dam to 112 on the output grid that was made from the 110 meter sequence. So, I built the dam up to 110, I poured tailings. Now I want to put that raise on top where, the dam's already built to 110 and tailings are already present. So in order to sequence this properly, I have to change this grid here where I'm going to raise my dam, and I need to always raise my dam on the output grid from the previous iteration. Okay, so let's take a look at this. Okay, so these dots and backslashes, this is basically indicating how many folders I want to go back. Okay, so I want to go back one folder into a location I'll name later. And I want you to grab the output grid, .m grid. So I always want to be getting the output grid from the previous folder. Okay, so what's in here? It's going to be a folder called previous elevation. So these squiggly brackets, I'm dictating what's going to be written inside these squiggly brackets with this dot format function. So I want you to go get that previous elevation. I want you to go back to the previous folder. Go back a folder. Go look in 110. And grab the output grid. When you're in 112, or when you're in 114 now, go to 112, go grab that output grid. When you're at 120, go to 119, go grab that output grid. Use that one. Always use the output grid from the previous iteration to raise your dam on. I want to note what the dam fill volume is at every iteration. So I'm just going to create a new variable here, call it dam fill volume. And just note what the fill volume is. Then I'm going to clear my graphics. That's fine, I clear my graphics every time. Otherwise, your screen's just gonna continue to have layers on it through the different crest elevations. Now I'm coming into my deposition here. All right, so base grid. Do I always want to deposit tailings on the grid plus dam surface? Yes, I do. So for every iteration, it's going to apply the template. It's going to raise my dam. It's going to create a folder called centerline in my working directory. And within that centerline folder, named after my dam template, there's always going to be this grid plus dam surface. And that's always going to be valid. I always want to pour tailings on a grid plus dam surface. And the grid plus dam surface in every iteration is going to be, my output grid from the previous iteration with that new lift on is going to be my grid plus dam surface. And that's always where I'm going to want to pour tailings. I don't have to worry about, and I'm always going to use also the dam discharge line in that dam template folder. So it's the advantage of using the dam templates here is it's always creating that discharge line. It's always creating a grid plus dam surface in a set of, in the folder named after the template. So it creates a structure that you can repeat. So everything's always going to be organized the same and created the same. Everything's just getting sent to new folders named after the elevation. All right, so I don't have to worry about a dam discharge line offset. My fluid volume isn't 400,000 every time. It's going to be this variable here, fluid volume. My initial discharge elevation, I'm going to say it's my crest elevation, which is elevation, -1. I'm always going to be discharging 1 meter below my crest elevation. I don't have to worry about max change. I don't have to worry about max iterations. This is defining how the software is running through the different iterations. So my max pond elevation, I'm going to say is also elevation -1. So that's your maximum containment elevation. Where do you want to consider you have containment up till? I'm going to say it's crest -1 again. Don't have to worry about these. Once again, just defining how the software is iterating through different options. Okay, pond elevation. So this is where it's asking you for that guess. What do you guess the pond's going to be at? Not necessarily where the pond is or, your maximum contained, but what do you guess it's at? So we can start iterating from there and try to figure out, how to fit in the 400,000, 700,000, 1 million cubes. Well, I'm going to say always guess 5 meters below my crest. Just always guess 5 meters below my crest. Pond tolerance. So 1% error tolerance, keep that in there. Pond location in X, Y, and Z, that doesn't change. It's always in the same spot. More kind of accuracy or iterative options here we don't have to worry about. And then the tonnage. So our tailings tonnage, which we call tonnage. So that is going to be variable. Okay, so now we've made the deposition dynamic. Or once again, we're going to clear graphics. And then we're going to get into appending with color. So once again, a lot of this can stay the same. We're always going to be modifying that original image at this location, that PRH. That's not going to change. Every time we're going to take that new line work, go to the original image, edit it. The dam footprint is always going to be in that centerline folder named after the template, and it's always going to be called footprint.mcurve. And we can select this color every time for consistency. The tailings outline is always going to be in your working directory. So that's fine. The only thing we really need to change is the output image name. We can't name them all, 110. So in this case, we're going to name them image, squiggly brackets, whose content will be determined later, and it'll be determined after this format statement. So format, open bracket. So now we're directing what to put into the squiggly brackets here. Not sure if they have a more official name. I call them squiggly brackets. So format, string. I'm going to take this now, we're going to make it into characters. String elevation. So whatever elevation you're at, call the image that. So image 110, image 112, image 114. That's the only thing we need to do here to make this dynamic and applicable. Otherwise, it would create an image called 110 meters every time. Not the end of the world. You're not overwriting the image because it's going to write it to the working directory, and the working directory is going to be changing every time. Because you've defined it up here, but it'd be a little sloppy to call it 110 or just name it the same every time. Okay, then for every iteration, we are going to open up that output grid. We're going to drape that image on the output grid, but we don't necessarily want to drape, image 110 every time. We want to drape this image. So we have to change this here to align with the fact that the image isn't always going to be called 110. So same approach. Just going to modify here, make the name dynamic, squiggly brackets, .jgw, dot format, string, elevation. And we're always going to be draping it on that output grid. The output grid's just in different locations as we work our way through. Every time we can open up the pawn surface in the working directory, that's fine. We'll always go back to viewpoint 1. And then we want to save an image. Again, the only issue here is the labeling here. We don't want to call it 110 meters every time. It's going to overwrite. So we need to make this dynamic. So instead of calling this screen grab 110, again, squiggly brackets. So it's going to be something, screen grab something, screen grab underscore something dot JPEG. And then we'll define that something here with the format function. Format, again, string, elevation. Okay, so at the end, I want to clear my graphics again. So I'm just going to polish this off with another clear graphics. And then I'm going to close my loop. So when the previous elevation equals elevation, we're done. And close that loop. So here, as I apply this clear graphics, if something is on the screen as unsaved, it's going to ask me, do you want to save it? I don't want to have to hit OK every time to clear my graphics, so I'm just going to ask it not to ask for every clear graphics. I'm just looking for my clear graphics here to modify them. So there's one here, clear graphics. Here, I don't want to be asked. Just clear my graphics every time, no matter what. Again, clear the graphics. Right now I have a dynamic script. Let's save this in my 𝐓𝐸 folder. Call it training. And let's see if it works. I'm going to come here. I'm going to clear my graphics. So right now, one important thing to remember is I want 110 to be my working directory because I wanted to go look in 110 for that output grid. Where did it save my script? Let me just check that. I went to a completely different folder. Let me fix that. Right there it is. So take the script, drop it in. You can see here it's going to run through the different iterations. Okay, so it started with 112. Based on the tonnage and pod configuration that we entered. Let's see to figure out how that works. Okay. That was pretty quick, but draped, appended, took a picture. That's going to go through 114. So you can see there it's doing the deposition, creating the appended satellite image, draping it, taking a picture, saving it, moving on to the next iteration. So it's just going to run through 116 now. Then 117, 118, 119, 120, 121. So we're well over time. But I think this gives you a good idea of, the benefits of automation. We're going to do a lot of different lifts and determine volumes. Uh, get a lot of imagery done very quickly. I think we can take this script and then next time build off of it, add a user interface, so we can start to vary, the the pod volumes that we want to enter. Maybe we want to do a different range for the crest elevations, different range for the tonnages. So as opposed to hard coding them into the script, we'll create a user interface where we can enter those values in and play with them from there. I'll add this script. I'll send the script out. It'll be available with the video, so you can download the video, you can download the script or watch the video and take a look at it. And then I think in the next iteration, take this script and make it really even more useful, more dynamic, the ability to change different values around and add some additional features to it and output results to Excel and PowerPoint and things like that. Okay, it's going to do the last one here. Okay, so we see it's done. We look back here. You can see every folder now has been created. Within our main root training directory, folder for each lift. If we look through, within each folder, we have the imagery created and the screen grab for every period. So that's our viewpoint. And just take a look at the outputs here. You can see it's run through every trial. Okay, so I'll post the video. I'll post the script online. Next time, I think we build off it, start adding different functionality to it, user interface, output results directly to Excel, maybe PowerPoint as well, and just continue to add functionality. But this is the process. You do things in the software, macro record it. Once you're done, take that piece of script, take your variables, take those fixed inputs, make them dynamic, and then just start stacking things together until you have a workflow that's really automated. And it's all about, repeating that structure. So one, creating the new deposition run in 𝐓𝐸𝐬𝐬 to have structure to your folders. Then when you're applying a template, everything's named the same. Everything's going into your working directory. When you do a deposition run, everything's always going to be called an output grid. You're always creating tailings outlines. So because of how the software works, because of that structure that it creates, it makes it easy to automate workflows like this. I will email out the recording. I'll post it on LinkedIn. If you're not following us on LinkedIn, please do Muck3D. As well, it'll be part of the newsletter that's going to be coming out next week. I'll email that as well. If you're not on the newsletter, if you're not following us on LinkedIn, I can email it to you directly as well. But there'll be a link to one of the videos posted on YouTube, and there'll be another link uh, if you want to download it off SharePoint or also watch it on SharePoint in case YouTube's restricted for you. Thank you, Sebastian. Have a nice day, and thank you guys.